much math. So I feel like just like, yeah, I think it's gonna be similar to 6501. That's kind of what I'm expecting, or hoping, I guess. Maybe. But like, I think it'll be less tricky. Like, I don't think he's gonna write nearly as like nuanced questions. So yeah, for sure. I'm cool with that though. Like, I don't care about business. Like, I'll leave that to the MBAs. It's the worst. Yeah, it's terrible. And I've like been attending this class, but not really. Like, I've been sitting here all semester. Well, I am not much farther along. Like, I've been here, but after like the second week, I was like, started slowly tuning out. Pretty much, yeah. Yeah.
Good morning, everyone. Let's start the class. Right, today let's first quickly recap on the last topic. Point out some, important issue to just, refresh your memory, and then we're gonna quickly go over the exam. The format, what you can expect in the exam. So let's first quickly review what we talked about for the last topic that we discussed last week. This endogeneity issue and how to address it. Right? So by addressing this endogeneity issue, we can perform the so-called causal inference, the causal analysis. Right? So you can review the causality. Right? So again, then we how to deal with. There are a lot of different types of endogeneity issues. Right? So caused by different sources. And there are different ways to address those endogeneity issues, right? So, but we don't, if you want to learn that, you can take like a 5-year PhD study, to struggle with those issues. But here we only talk about one solution, okay, one particular approach that we can address this endogeneity issue. This is called instrumental variable. Right, and then we, review the endogeneity issue. Where does endogeneity issue come from? Many of you asked about how should you prepare for the exam, right? So for the exam, just focus on the key concepts for each topic, right? So for example, each topic, what is the problem that we want to address, right? And what is the cause, and how did we, what method, what model, what method did we propose? Those on the high level, right? So the first order, those like conclusions, those properties, those issues. Right? So review those, and then you should be able to, once you understand all of them, you should be able to answer those questions easily. Okay, those questions actually are quite straightforward, just based on checking your understanding of those key concepts. For example, this one, right, endogeneity issue. You need to understand what is endogeneity issue. Right? I can describe, right? I can easily write a question, describe, asking you what is the endogeneity. I give you several, choices. Right, so describing what is the issue, so you need to be able to figure out which one is the correct description, right? Things like that. So endogeneity is basically the source is what? Now the standard assumption is that x variable, right? All the x variable, roughly speaking, right? So this error term need to be independent, uncorrelated with all the x variables. So no matter what values this x variable take, right? For each observation, the expected value of the error term is always 0. Right? And one observation has a higher value for that particular x variable, it doesn't affect your expectation of the error term. The expected value of the error term will always be equal to 0. Right? This is the standard case. This is the case free of endogeneity. However, if this assumption doesn't hold, then you run into this endogeneity. Right? If some observation has a higher value for a particular x variable, as a result, the expected value for the error term will be different. And then, we say that there are endogeneity issues. In other words, endogeneity issue means that a particular x variable or several x variables is correlated with this irritant. All right, if one x variable is correlated with this irritant, we say that this particular x variable is endogenous. All right, so the example we talked about last time is that education, right? Education, so years of education a person takes, actually it's a choice variable. It could be associated, correlated with many unobservable factors that will affect a person's, y variable. Y variable here, the y of interest is the earning ability of a person, right? So those, there are many unobservable factors that will affect a person's earning, but those unobserved factors, variables, will also be correlated with this individual's choice of staying in school for how long. Okay, so as a result, we run into this endogeneity issue because this variable is not observed, so it's part of the irritant. But if, part of irritant means what? Irritant always affects y, right? Because that's by the setting. So irritant always affects the outcome. Irritant are all those unobservable factors that will affect the outcome, but not included in your observed x variables. Right? So irritant should always have an impact on y. Otherwise, it shouldn't appear in the equation at all. Right? Irritant should always have an impact on y. But the standard assumption is the irritant should be uncorrelated with this x variable. But in our case, if this is the variable that's missing entering the irritant, then this variable will be correlated with the education with the x variable as well. As a result, it creates this endogeneity. Okay, as a result, this years of education, this x variable that we observe for different individuals become an endogenous variable. All right, so that's that. So we said that there are actually a lot of different sources of endogeneity created from different sources, but what we are going to focus on is this so-called omitted variable, just like what we said. Some variables that we do not observe, right, so that they enter the irritant, but those variables will be correlated with this endogenous x variable. Okay, so those are the sources. So this is the main source of endogeneity. Although there are other sources of endogeneity, but this is the most common, most the most commonly encountered, right? So that's the source. And we talk about that, right? So then with the presence of this endogeneity, or the potential endogeneity, so how will this estimates of those beta coefficients be biased, right? So we discussed that. This is something you need to understand, right? You need to be able to figure out what is what's the direction of the bias, right? For example, the direction of the bias depends on what? Depends on the relationship between this particular, let's say, again, we focus on the case of missing variable, omitted variable, right? So one variable is, you see, it's unobservable, it's omitted, right? Unobserved. So as a result, it will enter the irritant. Again, it will have an impact on y. And let's say this x variable is correlated with this particular x variable, right? Which creates this endogeneity, because this is the irritant, right? This combined is the irritant, and then now the irritant is correlated with this. And then, how will the presence of this potential endogeneity issue bias the OL estimate of this particular beta? Right, this you need to be able to figure out. For those of you who have already completed the homework, we have the questions about that, right? So you need to be able to figure out, I mean, you can pretty expect that you'll see similar questions in the exam as well, right? So to tell you how this is related to this, how the other variable is related to y, and what the direction of the bias of that OL assessment.
Do we always know what we're trying to account for in the error term to figure out what the correlation should be between the omitted variable?
You do not know. So, but assuming suppose this is the correlation, you should be able to tell the direction of the bias. Yes, but because it's omitted. So what really this direction is, how this omitted variable is really impacting y, and what's really the direction of the correlation between this omitted variable and this endogenous variable. We do not really know for sure, but we can just anticipate. We just suspect what is. But suppose you know the direction, you should be able to clearly say that what is the direction of the bias. All right, so again, what's the rule? Basically, it first of all depends on two things, right? Depends on how this omitted variable itself is affecting y. What's the correlation between this omitted variable itself and the outcome. Is the omitted variable positively contributed to the outcome or negatively contribute to the outcome? All right, so that's the first thing. So that's the sign of this beta k. Okay, and then another thing is that depends on how this omitted variable is correlated with this endogenous x variable. It's whether it's positively correlated or whether it's negatively correlated. All right, so that one is this sign of this delta j. All right, we said that this delta j is the coefficient if we run a separate regression, if we regress this omitted variable on all of these x variables, and the coefficient in front of this endogenous x. So that's delta j. So the sign of this delta j actually tells you what's the direction of the correlation between this omitted variable and the endogenous x variable. All right? So you see, that's the product. So it's very clear. So if this omitted variable positively affects the outcome, and that this omitted variable is also positively correlated with this endogenous variable, and then the bias you're going to get is positive bias. In other words, the OLS estimation will overestimate the true value of that beta coefficient. Right? So how to understand that? This is again, just think about this ability. Right, let's say the ability of a person, somehow we have a measure, of a person's innate ability, and this one is omitted, but it's in play, right? It's affecting a person's earning capability. So let's say this one, ability, is positively contribute to earning, right? Higher ability, higher earning, right? So beta k is positive, right? Let's also say this ability is positively correlated with years of schooling, years of education a person chooses to receive. Okay, high people with higher, again, quote unquote, somehow some measure of the ability, right? Higher ability, positively correlated to higher to number of education. So people with more, higher ability choose to stay in school for longer, choose to pursue, more advanced degree, right? So then, if that's the case, then this delta is also positive. And as a result, the regular OLS estimator, ignoring this potential endogeneity issue, will end up overestimating the true value of beta 1. All right, but again, make sure this is just the result, but try to intuitively understand why that is the case. Again, we said that ability, right? So you observe in the data, you just observe people have higher years of schooling, right? And then you observe people have higher earning. But actually, the underlying mechanism, the true mechanism is what? People with more years of education are likely to also have higher ability, right? Because the positive correlation. People with more years of education are likely to have higher ability. And then, but because this higher ability will also contribute to higher earning because of this positive beta. So as a result, you're going to observe higher earning, right? So this higher earning is a combined factor. One factor is the years of education itself contribute to the earning ability. But another factor, another mechanism is higher education is correlated to higher ability, and the higher ability also contribute to higher earning. But if you ignore this mechanism, the second mechanism, what would you conclude? You will conclude that all the increase in the earning is attributed to this larger, higher years of education. As a result, you're gonna overestimate the effect of education on earning. Is that clear? This is the mechanism to help you understand why we have this relationship. So again, to prepare this, you don't need to do rote memorization. You don't just memorize that as is. As long as you understand the whole mechanism, the framework, why things work this way, you should be you should be able to easily figure those results out. You don't really need to memorize all of them. All right?
I know that you just talked about this, but I'm trying to grasp how can an endogenous variable affect how some error term affect the endogenous variable in one way, but affect the final output in a different way? I know there was a quiz question on this on the homework, and I was having a hard time understanding it.
Yeah, so that depends on the context. It depends on what omitted variable you suspect is at play. All right, depends on the context. For example, this one, this is more like your suspicion. Because, like, I just answered to the previous question, you cannot really say for sure because it's, after all, it's an omitted variable. Omitted variable, you don't observe that. So you do not really know for sure what is the correlation, how is that correlated with y with, the other x value. You do not really know for sure. So it's more like your assumption. All right, so what we are talking about, these are sort of hypothetical examples. So if there is this presence of this omitted variable, if it is correlated, with this endogenous S variable in this way, in this direction, and then what will be the potential direction of bias? That clear? It's sort of like assuming that's the case, and what is the direction of the bias?
Could you have a situation where the ability negatively affects?
Yes, I mean, if that's the case, you should be able to say what will be the direction of the bias. Yeah, let's say if the ability, that's about the next example I want to discuss. If let's say this omitted variable ability, right, it is still positively contributing to this outcome, the earning. But let's say it is now, instead of being positively correlated with this endogenous X variable, it's now negatively correlated with this endogenous X variable. All right, so people with higher ability, they don't bother stay in school for long. Okay, so they may even drop, the college, right? So they start their own business. Let's say if that's the case, then what will be the direction of bias? Again, ability is still positively correlated with Y, but ability is now negatively correlated with this years of education. Then what will be the direction of bias? Then, if that's the case, if that's the true case, right, then your OLS estimator, ignoring this potential endogenous problem, will be underestimating the effect of education on it. Again, the mechanism is like that. Now you observe people with higher years of education, right? But then again, one mechanism is higher year of education itself will have impact on Y. Its only impact on Y, direct impact on Y. But indirectly, higher year of education now is negatively associated with ability, right? So then as people stay in according to our theory, people stay in school for longer, actually they tend to have on average lower ability. As a result, this lower ability will actually reduce the expected earning for those people. So overall, in the data, what you observe is people have higher years of education do not really earn that much. Right? So as a result, you would underestimate the effect of education earning because you also attribute that the negative effect from this hidden, unobservable disability also attribute to that earning, which actually reduce the effect of earning of education on earning, from your estimation. So as a result, you end up underestimating the true effect of education on earning, if you ignore the potential.
If you have two of the same coefficient, one which has the effect of the error term and one which is without the effect of the error term, the endogenous variables, how do you determine from the difference what the direction of bias is?
Yeah, that's a good question. So if, for example, you have another variable, right? You have two omitted variables. Each of them have different directions, right? Have those things. Then what is the overall bias, direction of the bias? Depend on the strengths. All right, so if one omitted variable tend to overestimate the coefficient, the other one tend to contribute to underestimation of the coefficient. Then the overall effect, whether you end up with overestimation or underestimation, depend on the strengths, depend on those values of those new coefficients.
Oh, I was just asking if there was only one endogenous variable and you just.
It's also then it's the overall. If it has counteracting effects, that's the overall. Whether, for example, in some sense, from some argument, it could be positively correlated with this one. Based on another argument, it could be negative with this one. Then whether on Earth it's eventually positive or negative, it depends on, again, the relative strength of these counteracting factors. All right, but again, when we discuss this, it's all hypothetical. Basically, we just assume that this is positively correlated with this one, and then what will be the potential direction of bias. All right, so we do not, without observing those variables for sure, no way you can really say for sure that what's the direction of the bias. Because the correlation, all unless you observe the data, you measure the correlation actually in the data, right? But if now that it's unobservable, so all our discussion is basically hypothetical. You had a question?
Yeah, so in your example with the low ability affecting the coefficient of education, right? So the ability is also supposed to be correlated with education, right?
Yeah.
So I don't know, like, are you supposed to find out whether the correlation is negative or positive looking at the coefficients and the bias? Or is that something like from common sense ability would be positively correlated with years of education?
Yeah, like I said, it's all hypothetical discussion, so more from the common sense.
Okay.
You won't really observe those. If you could observe those ability, those omitted variables, then the problem solved. You just collect data on that, then it's no longer an observable variable, no longer exists. The thing is we cannot really observe them, so all we can do is just reason based on common sense.
Okay.
All right.
I know there's a way we can re-estimate the beta hat using the IVs. Are we able to actually find what delta J is using the new beta hat using IVs?
Yes. Once you use IV, again, suppose the IV is valid. If the IV is valid, the IV estimator should be reflecting the true beta value. All right, that's true. So if you have this IV and the IV is valid, and then the estimated value, IV estimator of those beta coefficients is supposed to be, reflecting the true value of the beta coefficient. Of course, later we're going to talk about that. We say it's reflecting the true value of the true beta coefficient. It's in what sense? This is always keep in mind. We say, we have a beta hat, right? Estimate of us, the true beta value. But does that mean the beta hat that we get is exactly equal to this true beta value? This actually applies also to the regular standard linear regression. Standard linear regression, let's say we assume we are free of this endogeneity, so the standard linear regression works perfectly well. But then we get this OLS estimate of beta 1, right? Say that it's equal to certain value 1.2. But does that mean this 1.2 is the true value of this beta 1? No. The value we get makes sense, is correct in what sense? Given the data, related to that, don't forget the data sample we get is only one sample out of the general population. We said that all the estimates are what? Functions of your data. So if you draw another sample, you apply the same model, apply the same estimation method, you get another estimator for that same coefficient. Right? So in that sense, no way, every single estimator you get for this particular coefficient doesn't really equal to the true value of that coefficient. Then what are we doing? Then in what sense the estimator that we get is meaningful? In expectation. All right, it's only meaningful in expectation. It actually is equal to the true value of the true beta coefficient. What does in expectation mean? Just like if you repeatedly draw a random sample from the general population. Okay, you draw a lot of you draw like thousands of even millions of the random samples from the same general population, right? And then for each random sample, you estimate you perform this estimation, you estimate this coefficient, and then you get a lot of coefficient, and then you take the average over all these estimates, coefficient estimates that you get, and that average value will converge to the true value of that coefficient. All right, that's what we mean by it. So that's all those meaning of those beta coefficients. That's the beta coefficient. If free of all the potential bias, then the value is meaningful only in the sense that it will converge to the true value in expectation. Or it will converge to the true value if you repeatedly estimate that from repeated random samples. All right, so make sure you understand that's the basic idea of this. That's why we have that. You remember in those t-tests, what did we do? we need to evaluate the variance of that beta estimator. Right? The variance, I explained that, right? Where does the variance come from? Because given a data set, the beta estimator is fixed, is deterministic, because you have the formula, you can estimate it. Right? So then where does the variance come from? The variance comes from that fact, because every data set is a random sample from the population. All right, the variance comes from if you repeatedly draw data sample from this population, and then you keep estimating the model using the same way, using those repeated, using those different data samples, then you're going to get different values of this beta estimator, and it will have a variance. And over all this variance, but in expectation, its value will converge to the true value. All right, that's what it means. But for a single data sample, you get the estimated beta hat is almost certain is not equal to the true beta value. That clear? So make sure you understand the basic idea. All right, so but again, this is the direction. All right, so with this, you can easily see the direction. Things are a little bit trickier. If this omitted variable is negatively correlated to y, is negatively contributing to y, right? Something is like a negative factor. So if it's higher the value, lower that y. And then basically it's the opposite. Then if it's positively correlated with this endogenous x variable, then the OLS estimator will end up underestimating the effect of this one. Right? So that's why for the homework exercise, actually I asked you this question. Right? So after applying this IV regression, what did we say? What did we see? Yeah, I can tell you the outcome, right? So if you get the right outcome, we see that it's underestimating, right? So the OL estimator end up underestimating the effect. So the OL estimator of that beta coefficient in front of this year's education end up being less than the IV estimation, right? Let's suppose IV correct for that the bias. IV is correct estimation. Then the OL estimation, we found that from our data, it end up underestimating the effect of education on earning. Then I asked you about coming up with possible explanation of that. Then there are a lot of different explanations, but you have to fit this direction, right? Because it's underestimation. Then depending on what you think the omitted variable is. Some omitted variable could be positively correlated to y. Some omitted variable could be negatively correlated to y. Right? But then depending on that correlation, then if it's underestimating, then this variable should correlate with this x variable, endogenous x variable, in the right way, so as to arriving at this underestimation. So yeah, I'll give you, actually that is a good question. All right, so make sure you answer that question carefully, and then you look at the 4 possible explanations I gave you, right, the choice options. And then you see, okay, which one, for each one, right, what will be the sign of this beta k, what will be the sign of this delta k. All right, and then you figure out, okay, why one of them is the, correct potential explanation for that underestimation. Okay. All right, so then we talk about this. Then we talk about the IV, right? So the IV estimation, in order to correct for this potential endogeneity, we introduce, again, there are different ways, a lot of different ways. Some are like a matching-based mechanism, right? Some are, of course, the best solution is that we do randomized experiment. Okay, randomized, like the perfectly designed, well-controlled randomized experiment. But I said the last time, right? So this is actually the only way, the ideal way to to precisely tease out this endogeneity. But it sounds easier, than it can actually be conducted. So even though it's like a clinical trial, actually a lot of clinical trials, you cannot say for sure that it's perfectly controlled. It's like a purely randomized experiment. Because randomized experiment, you need to design that in an ideal setting so that the only variable that's changing is this variable of interest, whose effect you want to measure. Everything else is the same. You perfectly control that. Again, in real setting, it's never so easy. All right, so, if there's some other potential issue that will change with your experimental assignment, then, still, you are not totally free from this endogeneity. All right, you need to know that this, clinical trial, right? So, usually the randomized experiment, we have the so-called treated group and the control group. right? So you randomly assign all those individuals into one of the two groups. It should be totally purely random. But what you need to do is that to ensure that other than this group assignment, nothing else is different across all the individuals. Everything else is the same. All right, but if as a result of this group assignment, something else also changed, then those something else will enter this area and will cause this endogeneity. So even for those experiment design, yeah, actually a lot of experiments are potentially problematic. It's not like a purely random. All right? So that's why the true causality is really challenging to tease out. Right? So all those methods are not perfect. Every method has its own limitation. Right? So usually what we need to do if you really want to be confident about your conclusion, if you're really making a very important kind of discovery, you'd better try multiple methods, okay, to show that they all confirming the fact that what you have discovered is a valid causal influence. Anyway, yeah, so different methods, some are matching based, some are, you add some individual, control variable. And then, and then people also now do the synthetic control. You create like a hypothetical kind of matching sample, combining all lot of the different effects. And looking at the trend, before treatment trend. Those lot of methods, all right? So, but anyway, now we only focus on one potential treatment, that's the IV instrument variable. And the instrumental variable, the idea is the rough idea, these are the math, right? So the rough idea, we said that we just found those variables that satisfy these two requirements. One is called exogeneity. That's the most important thing, exogenous. So this variable needs to be exogenous. In other words, this variable needs to be uncorrelated, independent from that error. All right, that error including the unobserved factor that caused that endogeneity. So this instrumental variable need to be uncorrelated with the error. You need to ensure it. So the ideal case is that we find something totally out of the framework, out of the picture, something irrelevant. Like I said, you find the weather of that day, right? So then it fluctuates, by itself. It's totally random. So as a result, it has nothing to do with the mechanism that will affecting the y outcome, right? So in your original equation, it has nothing to do with that mechanism. So as a result, we can be sure that this instrumental variable will be independent from that error term, will be uncorrelated with the error term. Okay, so that's the foremost requirement, the exogenous requirement. IV, instrumental variable, need to be exogenous, need to be uncorrelated, or need to be independent from the error term. That's the first requirement. But that's not only the story. If that's only the case, it's easy to find. You just found like a totally irrelevant variable that will satisfy that requirement. Right? But however, the hard part of finding a valid instrumental variable is, like the two requirements need to be satisfied at the same time. The second requirement is the relevance requirement. That is, this instrumental variable need to be correlated with that x variable, with that endogenous x variable. All right, so this is actually in some sense contradictory to the first requirement, right? On one hand, it has to be uncorrelated with the error term. On the other hand, it has to be correlated with this endogenous x variable. All right, so that's why a good IV is very challenging to find. If you find a good IV, you can publish a paper, in the top. If you find a really good IV. All right, so again, uncorrelated with the error term, but correlated with the endogenous x variable. As a matter of fact, we want that to be the higher the correlation with the endogenous x variable, the better. You see, we want it to be highly correlated with the endogenous variable, but we want it to be uncorrelated with the error term. But because the error term is correlated with the endogenous variable itself, so that's why it makes it hard to find. It's sort of like contradictory to itself. So that's why it's hard to find. So for example, in the weather, right? If you believe weather has nothing to do with the error term, but this weather is better to have some correlation with this endogenous x variable. If that's the case, then it can be used as a good IV. But if it's also uncorrelated with the x variable, then it's irrelevant. It doesn't qualify as a valid IV. All right? So that's the requirement that it has to be checked. So then once you have the IV, how do we estimate that? So that's the basic setting called the IV regression or IV estimator. That's the general setting. The IV estimator, let's say we have these are our original regression, right? Original X variable we collecting our data. Let's say these variables denoted as Z, they are exogenous. They are okay, they are free from that endogeneity problem. The original is these independent variables, they are uncorrelated with error. But let's say these few X variables are endogenous. All right, each of them is correlated with the error. Again, you may not necessarily only have one endogenous variable, right? Sometimes you may have multiple endogenous variables in your set. So let's say these K X variables, they are endogenous. Then what do we need to do? How many IVs do we need to find? At least the same number of endogenous variables. All right, the number of IVs you need to find is at least equal to the number of endogenous variables you have in your original regression. All right, so if you originally you have K number of endogenous X variable, then you need to find at least a K IV instrument variable. And then what do? We can estimate the beta coefficients in this way because now each IV, right, is supposed to be independent from the error term, right? So then we can write this equation. The error term is y minus this thing, right? This is y minus this, so that's the y error. That's the estimate of the U. And then each IV is this. So we can use this as the so-called moment condition because it's supposed to be uncorrelated. So U and I, right? So it's supposed to be uncorrelated. So we can write out this equation. All right? And then for each IV, you have one equation like that. And then these Z variables, original Z variables, they are also uncorrelated. They are also exogenous. So you also have those equations. So as a result, how many equations do you have? You have, this many, right? So equal to the number of, you have this K plus 1 to K plus N, right? So this is from the original equation. And then you have this 1 to K. These are from the new IV that you have found. And then you have this, the first equation, right? This is just based on the fact that the average value of U itself will need to be 0. So as a result, how many moment conditions do we have? We have this K plus M plus 1, which is equal to the number of beta coefficient. So as a result, you have the same number of equations as the number of unknowns, number of beta coefficient. So then you can, by solving this system of equation, you can find the estimated value of the beta coefficient. Those are the so-called IV estimator. All right, so those are the IV with a direct definition concept from that instrumental variable, the validity of those instrumental variables. And based on them, we directly estimate the beta coefficient value through this system of equation. This is called IV estimate.
So with each instrument variable, because it's just correlated with the variable we already have.
Yes.
It would have its own new error term, correct?
Yes.
So when we use instrument variables to fix endogeneity, we are subbing out bias for more error.
Say that again. What's exactly the question?
I guess when we're going through this process, we are replacing the bias that we already have from our variables being correlated with each other by using instrument variables. So we remove that bias, but we've now just expanded the error term, correct? Because each instrument variable introduces its own error.
Yes. So that's why, later on we're going to see, there are two separate issues in your question. One is the error term, how to correct for the error term. So if you want to, say, measure the variance of the coefficient, the coefficient estimator, you need to be careful because later on we talk about this two-stage least square. The two-stage least square, if we do that in like explicit two-stage, just like you said, in the second stage you substitute the fifth value from the first stage, and then the error term need to be adjusted if you want to estimate the variance of the final beta hat from two-stage least square. All right, so that's one thing. So the error term, the variance of the estimator need to be adjusted to account for the fact that you do this two-stage system. This is one thing. Another thing, related to your question, I'm not sure if you are asking about that, is, later on we're going to talk about that. Again, related to my earlier point. What do we really mean by beta hat IV? This IV estimate of beta hat being unbiased. Right, sort of related to your question. Beta hat IV, right? The IV estimate of beta, right? So which is beta hat IV. This one is it's unbiased. Suppose our IV is valid, right? So then supposedly it is unbiased. But what does that mean? Does that mean the beta hat IV is equal to the true beta value? No, exactly, just like what I just said, right? It's unbiased in expectation. But in expectation, what does that mean? In expectation, right? So, but it varies. But the question is, it's one thing that it's consistent in expectation, but it's another thing that the exact value that we get, how far is that from the true value? That's totally different things, right? It could be unexpected, unbiased in expectation, but it could vary greatly, right? So then that answer related to your question, how large is the variance of the beta hat IV? If the beta hat IV, the variance is large, then even though in theory it's unbiased in expectation, but the exact one that you get from your data could be, you can expect that that's quite different from the true beta value, simply because the variance is large. Right? That's exactly the right intuition. Because with this IV introducing this, if your IV is not strong, later on we're going to talk about it. What does a weak IV mean? Strong IV means this IV is highly correlated with this endogenous X variable. Then the IV is strong. But if the IV is weak, if it's correlated with the X variable, endogenous X variable, but only to some extent, it's not highly correlated with the endogenous X variable, then we call it a weak IV. Then weak IV will exactly lead to that problem. It will increase the variance of your beta hat IV estimate. As a result, although still the expectation by theory, it's consistent, it's unbiased in expectation. But because the variance will be large, actually the exact value that you get from your data sample can be expected to be quite different from the true data. That's why people have this suggestion. If you cannot find a strong IV, you'd better not to use IV at all. Because weak IV is even more detrimental than ignoring the IV. You see the logic? Although weak IV in theory, in expectation, it's unbiased. But because the variance, it will increase the variance. All right, so the particular value you are getting can be expected to be very different from this beta. Even worse than the difference between a regular OLS ignoring this potential nonlinear. All right, so that's why weak IV is even more detrimental. So if you find that you want to use IV, you'd better find a good IV. Otherwise, just don't bother.
What was the reason behind setting the equation to 0?
That's called a moment condition, right? So this one equal to 0 is because the expected value of this u is equal to 0. This one equal to 0 because the expected value between z and the u should be equal to 0 as a result of that uncorrelation between z and the u.
And that's why you set every system of equations.
Yeah, this is called a moment condition. And then as a result, you have k plus m plus 1, number of moment conditions, number of the equations. And then you have, this many k plus m plus 1 number of beta coefficients. So the same number of equations as the number of unknowns. So as a result, solving this system of equation, you can estimate those beta coefficients.
Just to confirm something you said earlier, you said if you have k explanatory variables, you have this k instrumental.
Right. So if you have these many endogenous X variables, you need to have this many instrumental variables, so that the number will match. Right.
How do you know which of your variables have endogeneity?
Which of your variables? Yeah, it's your suspicion. It's your suspicion. You Yeah, but generally speaking, endogeneity issue is almost always present in all kinds of real applications. It's really hard to find a scenario, like observational data from your observational data that you say, you are free of endogeneity concerns. Usually it's always the case. But just how severe the concern is depends on different contexts.
So on the homework, we did have multiple variables, but the endogeneity issue is only expressed in one of them. So in the real world, we probably assume that all of the variables are affected by it.
Yeah, that's a good question. I think about it in the homework, we actually include the 2X variable, right? One is the education, the years of education. The other one is called the experience. That's the post-graduation experience. But, if you look at the data description carefully, how was the experience calculated? It's age minus education minus 6, right? So we're assuming that people start to enter school at the age of 6. So it's calculated this way. So in that sense, the post-education, post-graduating experience, that variable is mostly related to age, right? So in that sense, we think it's less, the age is sort of exogenous in a person's age, given that. So that's why we think it's less concern about age with this irritant compared to the correlation between education and the irritant. Because years of education is really a choice. Age is not a choice of a person. In that sense, it's less a concern. So that's why we didn't focus on the potential endogeneity issue for that experience level. You see? But of course, if we really want to be really thorough, we could also try to see how can we address that. There could also be, if you really argue, strongly, you could also say that there could be potential endogeneity issue between experience and the irritant as well. But yeah, because between these two variables, apparently the education, right, is more susceptible to this endogeneity issue. That's why we focus on that variable, for the exercise purpose. All right, that's good point. So, but notice that why in the homework exercise we add a quadratic term of experience, because we suspected that the age, right, the income level, the earning level can change with age, right, in the nonlinear way, right? So usually linear means it's always increasing, always decreasing in age, but we think that with the experience it could change in a nonlinear way. It can first increase and at some point it starts to decrease. So that's why we added this quadratic term of experience into this regression. So because we suspected for this experience variable, the nonlinear relationship is more of a concern rather than the endogeneity issue itself. All right, is that clear? So that for the education variable, we address that potential endogeneity issue. But for the experience variable, we address that potential nonlinear pattern by adding that quadratic. Okay, so that's the basic setting, the IV estimation. But then we said that this is like directly from the concept of the definition. In practice, when we address those, we apply those IV, we will address those problems. What we're going to use more is this so-called two-stage least square approach. All right, so the benefit of this two-stage least square approach is that it can allow us to include more IVs than the number of endogenous variables. So the basic IV, this one, think about it. How many instrumental variables can you include? Can you include less instrumental variables than the endogenous variable? Of course not, right? Because you need the same number of equations as the number of beta coefficients to solve that. So that's why the number cannot be less than it. But can you include more IV instrumental variables than the number of X variables? Yes or no? By this approach, you cannot, because if you include more the instrumental variables than the endogenous X variables, then you have more equations than the number of unknowns. Still, it create a problem. You won't be able to solve. You have too many equations, right? Then they cannot be satisfied at the same time. You see, so that's why the basic IV approach, it's only work for the so-called exact identification case. That means you usually have exactly the same number of instrumental variables and the number of the endogenous X. This is called exact identification case. But if you have more equations than the number of IVs, that's called over identification case. All right, if you have fewer equations, then the beta coefficients and the unknown beta coefficients, that's called under-identification. All right, so the basic IV estimation only works for exact identification case. All right, but the good thing about two-stage least square is that it works also for over-identification case. You can have more IVs than the number of endogenous X variables, and it will work as well. So actually, that's preferable. If you can find more IVs, the more the better. All right, but again, the precondition is that those are valid IVs, those are good IVs, those are strong IVs. If you can find multiple strong IVs, then the more the better. To include as many as you can find. All right, so that's always work better. So then you can do that. With that, you can do the two-stage least square. Again, we talk about how to do two-stage least square. Right, the first stage is regress this particular endogenous X variable or the exogenous variable from your original regression plus the IVs that you find. Okay? And then you get the fitted X value. And then in the second stage, you substitute the original endogenous X variable with the fitted value from the first stage. And then run that regression. And then the coefficient you get is the two-stage least square estimate. And supposedly it's unbiasedly reflecting the true value of the beta code. Again, it's unbiased in the sense of expectation. Okay. All right, and then, here, actually that's an interesting case that we want to discuss. Right, so this actually explains to you, go over those slides, all right? So this actually explains to you the mechanism, why this two-stage least square works. Right, so basically the two-stage least square, we run this one, right? You see, this is the original endogenous X variable. This is what? This is the fitted value from the first stage regression. Right, as a function of a linear combination of all those exogenous variables. The original exogenous independent variable from the original regression and also all those IVs. All those IVs are, by definition, they should be exogenous, right? They should be uncorrelated with the original error. So then as a result, this fitted X from the first stage is just a linear combination of all those exogenous variables. You see, just a linear combination of all those exogenous variables. Each of these variables, Z, right? These are the original exogenous variable. These are the IVs. So each of them are exogenous, are uncorrelated with the original error. As a result, the linear combination of all of them by design should be exogenous, should be uncorrelated with the original error. Right? So essentially, what you are getting, why you do this one, is that you purge the original endogenous X variable, right? Purge that. So that you only extract the exogenous component out of this original endogenous X variable. And then you leave the remaining difference. The remaining difference, this V here, that is the endogenous part. That is where it is correlated with the original error. And then you basically leave that into the new error. You push that into the new error. Right? So, you see? You push that V into the new irritant. It's V times the original beta 1. Right? So now this becomes the new irritant in your second stage regression. But this one is okay because by definition, right, all of them should be uncorrelated with both U and V. So as a result, all of them, this one and this one, should be uncorrelated with this new irritant. As a result, the second stage regression is free from endogeneity concerns. That's by design. That's by definition. So that's why it's valid. That's how you can do that. You can obtain the unbiased estimation. Right. Okay. Now, one final note on that. This we understand, right? So based on this setting, two-stage least square, let's take another look at why we need to, for that IV has to satisfy these two requirements, the exogeneity and the relevance requirement. Exogeneity is easy to understand, right? You have to assume, you have to ensure that this one, all of these should be uncorrelated with the U in order for this fitted X to be uncorrelated with U. Right? That's why you have to ensure that all these IVs that you found are exogenous. This is easy to understand because otherwise, yeah, you are just basically doing nothing because you replace the original endogenous variable with another endogenous variable. That's totally pointless, right? So that's easy to understand. But now the question is, why do we have to ensure this one is correlated with this X? The IVs that we found is correlated with X. Think about it. What the IV that we found is not correlated with the original endogenous X variable. Then will this whole thing, the two-stage least square, still work? Let's say I found an IV, right, totally unrelated with this original X variable. Then will this two-stage least square estimation still work? Why?
Because you're trying to replace the endogenous variable with the
Yeah, think about that. If it's uncorrelated with this one, what will happen to that first stage estimation result? This coefficient will be 0, right? Let's say for now we only focus on one IV, that the coefficient will be 0. Then the coefficient for that IV to be 0 from the first stage estimation, then what do we get? Then the fitted x1, right? Fitted x from the first stage is simply just a linear combination of what? Of those z variable that's originally exogenous from the original regression. Is that clear? If it's uncorrelated with the new IV that you found, right? So then this coefficient will be 0. So as a result, x hat fitted from the first stage regression will simply be a linear combination of those original exogenous variable in the original regression. Then what will happen in the second stage? Think about what will happen in the second stage. Yeah, I could ask you this question, right? So why, it has to be, what would be wrong, right? If Z1, if this endogenous S variable is uncorrelated with the IV you found, then what will go wrong in the second stage regression? What will go wrong? Second stage, then the first stage fitted X from the first stage is simply equal to this. Then we replace the original X with this into the second stage regression. Then what would be the problem? You see, this variable is now just a linear regression, a linear combination of them. And then you also have this same variable, same set of variables in the regression. As a result, what problem do you run into? Perfect collinearity. Remember, this one is essentially just a linear combination of all of them. So then the coefficient, and this coefficient, no way you can separately identify. Is that clear? So you run into this so-called perfect collinearity problem. Remember, we in the linear regression we did that, right? So variance VIF, that in the homework you did that, right? Calculate this VIF. If the VIF value is large, you have this collinearity problem. But if you run this one, you run the VIF, it will be infinity. So you have perfect collinearity problem. Because by design, this one is just a linear combination of all these variables. All right, so that's why we have this problem. So you cannot solve that problem. So that's why we have to ensure that at least there's some difference here. Some the collinear the in IV variable in the instrumental variable you find, at least it's uncorrelated with this variable. So at least this coefficient should be different from zero. That's why the relevance requirement is important. All right, so just from this example, you can complete this. All right, so then roughly that's the idea, that we talk about. All right, and then the R implementation, I'll just leave that to you. I explained well in the video, right? So basically, it's not too hard. We do this, right? We can explicitly do the two-stage least square, right? You first run the first stage, and then the second stage you use the fitted value, right, to run the second stage. But of course, we could also use this IV reg. But for the IV reg, the syntax is what I here. Right, the syntax, you need to use this pipe to show two parts, right? The first part are the original variables. The second part are all the exogenous variables. So original variables, of course, include some exogenous variables, some endogenous variables, right? And the second part are all the exogenous variables. So some of the original variables are exogenous, so you also show them in the second part. But then you replace those endogenous variables with the corresponding IVs that you find. All right, so you list the equation this way, and by showing listing all the variables this way, then the package knows how to do which variables can be treated as exogenous and which variables are endogenous and which variables are the IV. So it also becomes very clear, and it will perform that two-stage least square to do that to find the IVs.
Can you post like slides about the midterm review on Canvas?
Yes. Well, no, but it's not really about yeah, it's just some like formats, something it's similar to what I sent already in the advance. All right, so that's just the IV reg. All right, so then eventually ask you to compare the regular OR estimate and the IV estimate, and then see the directional bias, and then discuss the potential the exponents. All right, so that's just what we want to talk about for this IV regression. Now let's quickly go over the midterm exams. So as we know, the next class, right? So the regular class time, the same classroom, so 75 minutes. Yeah, so about that. So don't be late because we don't have much time. There's another class afterwards. So I may be able to give you a few minutes. When the class is over, but we can, extend for too long because there's another class coming in. So don't be late. All right, we have to start right at 11. And you may need to, I think it'll be fine. The multiple choice questions, someone asking me how many questions. I haven't finalized the final questions yet, but I'm thinking about like around 35, 36 questions. So roughly you have 2 minutes to answer each question. All right, some questions are no-brainer, just by looking at that you can quickly find the answer. But some questions you may need to read and study. So on average, I think 2 minutes one question. So that means you don't really have, if you're not really familiar with those concepts, you may feel a little bit of time pressure. So that's what means don't be late. All right. So but if you are familiar enough, a lot of questions can be, for me, for example, I can answer all the questions probably in 5 minutes. Yeah, but again, so it depends on, so that's why don't spend too much time on this the cheat sheet, because you won't have time to really look through the cheat sheet at the time. You don't have time to review all the concepts at the spot, right? So you have to already be familiar with those concepts. But on the other hand, don't be nervous, right? So some students sent me, told me that, oh, they feel nervous. Don't be nervous. Actually, the question is not very hard. Did you see my example questions? Actually, that will be about a similar style, similar level of difficulty. All right, so it's more like just asking you, like I said, the first order concepts, the main concepts that you need to be aware for each topic. So if you've been followed through this entire course so far, carefully on each topic, you understand all the concepts well for each topic. Pretty much, the review, the preparation is just, just straightforward. It's just a breeze. Basically, just go over, just refresh your memory about what each topic covers, what are the main issues, right? Each model aims to address, and what are the basic setup, what are the key assumptions, what are the key conclusions, the results. That's it, right? Because like I said, I won't really test you the derivation, each step. But still, in order to understand all of them, right? What this model is addressing, right? How it's set up, why do we have all those conclusions, all those results? You need to understand that where it comes from. Right, so the derivation, the setup. But like I said, this, if you've been following this all the discussion or lectures all the way through, you already understand that where they come from, right? So then all you need to do is just quickly review all those things. So it won't be too hard, just once you understand the main concepts, you'll be fine. But on the other hand, it will have like a comprehensive coverage. Basically, all the topics that we have discussed, you'll see some questions. So that's why, if you really want to do well, be sure to review all the topics. You cannot skip like one topic and you'll miss some questions. Right. And yeah, question.
Is that all topics including today?
Yes, including the IB. Yes. All right, and like I said, closed book, closed note. So no digital device, right? You cannot bring iPad. You cannot bring smartphone. Okay, no digital device. So you create this cheat sheet. So cheat sheet has to be on physical paper. All right, you can type that, or you can print that, or you can handwrite. Either way is fine. No restriction on the font size, and yeah, but it has to be a cheat sheet. And the size is just the letter size. The standard letter size, and you can do two pages.
We won't need a calculator.
Yeah, you don't need a calculator. You don't need a calculator. So no calculator is allowed, and you don't need it. Okay. And we're going to use Scantron. It's all multiple choice question. We're going to use Scantron, and yeah, bring an eraser as well, because make sure the eraser works well, because you don't want a smudge, like that, then it will ruin the
You're providing the Scantrons, right?
Scantron, yeah, I'll provide, but you bring the pencil. Alright, so you bring it. I may prepare some spare pencil, but I will not have so many for everyone. So the pencil, yeah, I think a regular pencil is fine, but 2B is better. Alright, so but as long as you mark them dark enough, the machine should be able to read that. Yeah, like I said, this is the questions and everything, including the homework. But you see the questions about the homework. And the homework, I will mainly ask you the key code that you should be familiar. So as long as you've done homework, you should be able to have, even if you don't really review them, you should have no problem in answering. All right, so that's the level of the code knowledge that I'll test. So yeah, but you do need to know. I will show you some. I show you one example question, right? So I may show you some printout from the R output, right? You should be able to read that, because that's something that you get in the homework. All right, those are the questions. We can take a quick look at do you have any questions about this example questions?